In this video, we'll go on a journey that begins with breeding cows. We'll then pass through the world of bases, both solidifying our understanding of them, but also extending it to include fractional bases. We'll then use fractional bases to solve the cow breeding problem that we started off with. We'll then generalize these methods to include a variety of related problems, and take some time to appreciate irrational numbers in a way that they're not often taught. Ready? So you're playing Minecraft and have a humble 2 cows. I know, but bear with me. Each day you take all the cows, pair them up, and for each pair you breed them to make one baby cow, which will become fully grown by the next day. If you have an odd number of cows, one of them will just have to sit out. This is how the population of cows evolves over 7 generations. Let's write this more mathematically, where C of n is the population of cows on day n. For days when the population is even, we gain another half as many as before. And when it's odd, the amount we gain is half the number of cows minus 1. And we combine this into one big formula. Either by hand or with a computer, we can calculate the first however many values of C. The difficulty in producing an explicit formula for C of n is that whether C of n minus 1 is odd or even cannot easily be predicted. Here, have a look at the first few values of R of n defined as the remainder when C of n is divided by 2, i.e. whether it's odd or even. Once we have C of n, it's trivial to find R by taking C mod 2. What's interesting though is that you can use R of n to find C of n, and it turns out that the explicit formula that we're working towards does just that. Let's explore C of n further though. We can plot the first few values of it on a graph, and the graph looks exponential. Given that with an even population, C increases by a factor of 1.5, and for odd it's just less than that, we expect 1.5 to be the approximate growth rate. Let's consider 2 simpler examples. Firstly, if pairs of cows bred to make 2 offspring each generation, the population would just double. And if they never bred, the population remains constant at 2. We can then see that C of n is sandwiched between these 2 graphs, of growth rates 2 and 1 respectively. So the growth rate of C will be somewhere between 1 and 2. If we plot a graph of log C against n, it tends towards a straight line, and if we were desperate to find the growth rate, you can approximate it like so. So we've used a visual technique to show that C of n is approximately exponential, but we have a problem. C of n is an integer sequence, and 1.5 to the n is not. To resolve this issue, we'll explore writing integers in base 3/2. We seem to take for granted the fact that we can represent any number on the number line with a string of digits from 1 to 9. Positive integers, negative integers with a minus sign, terminating decimals, non-terminating decimals, repeating decimals, and irrational numbers. Even complex numbers if we add in I times the imaginary component. In the decimal system, strings of digits carry with them an implied sum of powers of 10, positive powers to the left and negative powers to the right. So for example, 21.5 base 10, and that's what this subscript means, equals 2 times 10 to the 1, plus 1 times 10 to the 0, plus 5 times 10 to the minus 1, or 5/10. Binary is another base system that people are familiar with. Here we have a sum of powers of 2, so 10011 in binary is 19. Quick side note, it's almost impossible to talk about different bases without base 10 language and notation seeping through, written or spoken. But for this section, try as hard as you can when I say the number 10, for example, to imagine 10 items, be it apples or shapeless blobs. It doesn't matter that 10 is written 10 in decimal, 1010 in binary, spelled TEN in English or DIX in French. Just imagine 10 items. Now visualize the columns, or powers of B, base, as blobs of different mass. And I use the word mass in the most general form. That is to say that if we were working in base 10, 10 blobs of mass 1 is equivalent to 1 blob of mass 10. They're the same. This goes for base 3 or any base. So let's say we're trying to write 11 in base 3. To get the string of digits representing 11, only using the digits 0, 1 and 2, we start off with 11 blobs of mass 1, or 11 blobs in the ones column. This representation is called the exploding boxes model, and here the size of the blobs doesn't matter. Just remember that moving to the left, the mass increases by a factor of 3. This means that for every 3 of these blobs, we can replace them with 1 in the next column. These 2 are left behind, but that's okay because we can use the digits 0 to 2. Now we simplify further, replacing these 3 with 1 in the next column. We can now no longer simplify, so we're left with 1 of mass 9, none of mass 3, and 2 of mass 1. Indeed, 11 equals 9 plus 2. Now what's to say that these blobs must be integer multiples of each other? It's just as acceptable to say that moving from one column to the next, you can multiply or divide by a fraction. This is how you'd write 11 in base 3 over 2. Here, 3 in one particular column is now worth 2 in the column to the left, and vice versa. Therefore, 11 base 3 over 2 is 2102. And you can convert any integer into base 3 over 2 with this method. Using the exploding boxes model, we can do much more than just base 3 over 2. In the description there's a link that describes how to write negative bases and even imaginary bases, but these won't be relevant for our story. In base 10, 0.9 recurring and 1 are equivalent. Recurring numbers also show up in base 3 over 2. Take the number 2. We can write it as 0.3. Remembering that we only want to use the digits 0 to 2, we write 0.3 as 0.1 plus 0.2, and again we can convert this 2 into a 3 in the next column. What these square brackets mean is that it doesn't matter what column a 3 is in, it can be replaced with a 1 and then a 3 in the column to the right. Now continuing with this process, we see it keeps on repeating, creating a recurring string of digits. The trailing digits contribution to the overall number as you continue tends to 0. You're multiplying the trailing 3 by a smaller and smaller number, so the limit of 0.1 recurring is 2. This is just like how 0.9 recurring in decimal is 1. Now for 3, we can just add 1 to 2 to get 1.1 recurring. Where it starts to get interesting is the expansion of 4. We can use the exploding boxes method from before, but since we're moving to the right, the mass of the blobs is decreasing, so we must multiply the number of them by 3 over 2. The 4 multiplies to make a 6 in the next column, which will turn into 9. And then because 9 is odd, we'll move along the 8 and keep the remainder of 1. As this process continues, the number in the final column will keep increasing. This is something that doesn't occur in integer bases. As such, when writing this numerically, we need to slightly relax our rules on representing numbers. We are treating numbers larger than 9, here it's 27, as though they occupy a single column. This is no more problematic than any single digit number greater than 2. It just seems this way, because in decimal we are ultimately restricted to 10 unique digits. So at each stage we're multiplying the even part of the last digit by 3 over 2, moving this to the right and leaving behind any remainder of 1. As we continue, 2 things appear. Firstly, the digits before the last give the first n terms of r of n. Secondly, the final digit is 3 times c of n. Feel free to pause the video and figure out why this may be the case. For this, it makes more sense if we use what we learned from the expansion of 2 to write 4 as 2 times 2, or 0.2 recurring. For each of the 2's, we're replacing it with a 3 in the next column. Then we remember that any place we have a 3, we can replace it with 1 and then a 3 in the next column. We sum up all infinitely many of these to get a single 1 at the start, all the rest adding with each other to get 4's. Expanding in this way, it's clearer to see the similarity between the expansion and the problem. Any even digit multiplies by 3 over 2, and any odd number does the same with 1 less than it, and leaves 1 as a remainder, which is also added to all the next generations. Make sure you understand the link between the expansion of 0.2 recurring, base 3 over 2, and the problem. For the final recurring digit, it would be easier if it terminated, and we can use what we learnt before, that 0.1 recurring equals 2. Then here, for example, we can separate this term into the terminating and recurring component. We then rewrite the recurring 9 as 9 times 1 recurring, these 1's being equal to a 2 in the column to the left. Now we can see that this is the same as in our previous expansion of 4. For the final piece of the puzzle, we need to introduce the constant little r. This is the number such that in base 3/2, the nth digit of r is big R of n. Any approximation Rn or R subscript n is the first n digits of R. Now this is quite a few terms, so before we finish the problem, let's recap what we've got so far. C of n is our original sequence, the population of cows. R of n is whether C of n is odd or even. Little r is the constant with digits R of n when written in base 3/2, and Rn is R to n digits. Going back to the previous expansion of R, we can see that the 0.0100 is R4, the 9 is C of 5, and 0.0002 is 2 times 3/2 to the minus 4. Rearranging, we get this equation. This 3 now explains why previously the last digit was 3 times C of n. Now this was just one of the expansions. The same applies for all of them, so we can generalize the 5 to be n and the 4 to be n minus 1. We finally rearrange to get C of n, and this is our discrete equation. For the final analytic formula, we need to do some error analysis. I won't go over all of it. If you want, you can work this through, but there are a few key points to consider. Firstly, think about the difference between R and its approximations Rn. If Rn is R truncated after n digits, R must be greater than all values of Rn. Thus replacing Rn with R, we're subtracting a larger number, so the fraction will be smaller. The second important point is that this difference between Rn and R decreases on average by a factor of 2/3, and this is cancelled out by the 3/2 to the n, nicely leaving the error trapped between -1 and 0. Therefore, rounding up or applying the ceiling function, that's what these brackets mean, the error goes to 0 and we get the promised analytical formula for the exact value of C in terms of n and the irrational constant r. Ignoring the ceiling function, the growth rate is 3/2, and plugging in r equals 0.755 in decimal, we see that everything's multiplied by approximately 1.08. The ceiling function is responsible for the slight fluctuations, but as C gets suitably large, this becomes negligible. With enough cows, it doesn't matter whether there's an odd or an even number. Phew, that was a lot. What have we done? We started with the sequence of reproducing cows, learned that the sequence was exponential with growth rate 3/2, then looked at base 3/2 to learn specific information about the evolution of the sequence. This basic problem-solving technique can be extended past the original cows problem. One of the possible extensions is the mortal cows problem. What is the growth rate if cows die? In order to generalize, let's make sense of how you would think about choosing base 3/2 for our problem. To model the population of cows through the expansion of some number in some base, we need to use a base in which 2 equals 0.1 recurring. The interpretation of this is that 2 cows will produce 1 baby cow each generation, and this goes on forever. Given the equivalence between generations and powers of b, the base, we can then form the equation 2 equals 1/b plus 1/b squared plus 1/b cubed, etc. The right-hand side is a geometric series, for which we know the equation for the sum to infinity. All we need to do now is plug in a, the first value, and r, the ratio, both of which are 1/b. A bit of algebra later, we're left with b equals 3/2, which is just what we expected. Base 3/2 is the only base that suitably models our problem. Let's consider mortal cows now. Say they live for 3 generations. A clear way to represent this is with newborns as 0. Their ages will increase by 1 each generation until 2, after which they die. And they breed in just the same way as before. A pair of cows will produce a baby cow for 3 generations, so we need a base in which 2 equals 0.111. We then write this in terms of our base b, which gives us a cubic equation. Let's do a deep dive into cubic equations. Only joking. So I use Wolfram Alpha, and well, yeah, this is our real value of b that you get. There's not much to say about this number. but note how naturally this pretty disgusting base popped out of the maths. Given this framework, we can even revisit the Fibonacci sequence. Say you're modelling the population of bacteria, which reproduce on their own for 2 generations before they die. Like so. Note that the population increases with the Fibonacci sequence. Here, you would use a base in which 1 equals 0.11. Again, you solve for b, and it's not all that surprising that the golden ratio pops up, given the relation with Mr. Fibonacci. We can use this method to find the terms of the Fibonacci sequence analytically. Just like with our analytic formula for c, you can jump straight to the nth term without having to calculate all previous values. Now, I've only briefly shown you these 2 examples, and I'd encourage you to work through them. However, hopefully you can now see that this method can be used for some more well-known problems. More importantly, you can now see that base 3/2 wasn't just plucked from thin air. This, like so many other techniques for solving problems, is just that, a technique, a different way of looking at a set of problems. Something that many of you will have noticed, indeed you may even be shouting at your screens because of it, is that solving our immortal cows problem, there is no point in calculating the terms of c one by one and using this to find the approximations of the constant r if we are then going to use this r to find c. It will require at least as many degrees of precision. And yes, for one problem, this is incredibly inefficient. However, this can be said of any rational number. The original method of approximating pi involved calculating the perimeter over the length of the longest diagonal for regular polygons as the number of sides approaches infinity. This approaches the circumference over diameter of a circle, i.e. pi. You could ask, what's the point in calculating pi from the ratio of circumference to diameter if you're only going to use it to find the circumference of circles from their diameter? But you'll know that pi pops up in so many equations, calculating so many things across all areas of maths. You only have to approximate pi once to a suitable degree of precision to approximate the volume of a cone, for example, or the time period of a pendulum. Furthermore, once we get more efficient methods of calculating pi, for example, Newton's method, we can immediately use these more precise values in all of those equations. No need to go back over the original derivations. That is to say, embedded in any irrational number is the process used to find it. As soon as you find related problems, which to some degree have the same underlying process, you don't have to start from scratch. You can reuse the constants that show up in both. Now, the difference between e, pi, and the golden ratio and our constant r is that since the former are well established, you can just look up their values on your calculator or get billions of digits online. The question you should be asking is, where else does this constant r show up? As it turns out, the constant r appears in something called the Josephus problem. We have left a link in the description for you to further explore as you please, as well as documents and resources for everything that was mentioned in the video. On that note, we hope you have enjoyed this journey down the rabbit hole of cows, fractional bases, sequences, error analysis, irrational numbers, and I do say we. This video has been a collaboration for the Summer of Math Exposition 2.